All right, so here we're going to talk about binomial coefficients. So that's what this section is called. It covers a couple different things. It covers subsets, binomial coefficients, and Pascal's triangle. There's actually a few more things in this section in your textbook if you're interested in reading that, but these are the things that we are going to focus on. So for our first question, we're going to take the set A, which is the set containing the numbers 1, 2, 3, 4, and 5, and we're asked what is the cardinality of the power set of A? Or in other words, how many subsets does A have? So we've actually touched on this a little bit. You had kind of a similar question in your second homework assignment, but we never actually gave an explicit formula for how to compute the cardinality of a power set. So we want to think about it now. So what I'm going to use is the same kind of slot diagram that we used when talking about the additive and multiplicative principles. So basically, we're going to think about how many ways can we create a subset of this set A. So to create a subset, we basically need to say yes or no in terms of are we going to include or not to each of these elements. So there's 5 elements here, obviously, right? 1, 2, 3, 4, 5. So for each element, we're going to say yes or no to it being in the subset. All right, so in other words, for each of these 5 elements, we have 2 choices, right? Because we can say yes if we want to include the element, or we can say no if we don't want to include that element in the subset. All right, so we have 2 choices for each of those. And then the multiplicative principle says that we would multiply those all together, which is, of course, 2 to the 5th power, or 32 subsets. Okay, we can actually make this a more general rule. The question on your homework was if a cardinality of a power set has 32 subsets, what happens when we add an element? Well, that would essentially be adding an extra line here, kind of at the end of our equation, which would also have a 2 on it, which would increase to 2 to the 6th power. So in general, when the cardinality of a set A is equal to, let's call it n, then the cardinality of the power set of A is equal to 2 to the nth power. All right. So that's a good kind of formula there to remember. I'll even put it in a little box. All right, so if your set has n elements in it, then there's 2 to the n elements in the power set. All right, so the next question says how many of these subsets contain 3 elements each? So we're going to think about this in 2 different ways. All right, we know there's 32 subsets in total. If we wanted to, we could simply go ahead and list them all and then just kind of count how many of them have 3 elements each. Maybe we want to do it in kind of a more efficient way than that. So one way to think about this would be to choose 3 of the 5 elements to be in a subset, right? So if we did that, we're going to choose 3 elements, so we draw ourselves 3 blanks. Now, so this is like the first element, and this is the second, and this is the third. All right, so again, in these blanks, we're going to fill in how many choices we have. So since there are 5 elements in this setup here, I have 5 elements I can choose from for which element I want to be the first element in my subset. All right, so I choose whatever number that is. I can't choose that number again, which means I only have 4 choices for the next element, and then 3 for the last element. Again, we'd be using the multiplicative rule. So 5 times 4 times 3 is equal to 60. Now, wait a second. That's a problem because we just said there was only 32 subsets total. So how can there possibly be 60 that have 3 elements? So there is an issue here, is that this includes duplicates. This includes. So if you remember from our work on sets, if we have the set, let's say 1, 4, 5, that's actually the same as the set 5, 1, 4, and it's the same as the set 1, 5, 4, etc. So these are all essentially, not essentially, they are exactly the same set. We don't want to include it that many times. So how could we kind of get rid of these ones that we've overcounted? Well, we're going to take this value that we found, this 60. I'm going to erase all this just to give myself more room. Okay, so here we need to divide by the number of ways to arrange 3 elements. Right, because we have 3 elements in the set. Whoops, that's not how you spell elements. Right, and that would basically get rid of all that double counting that I just mentioned. So the number of ways that we could arrange 3 elements would be 3 times 2 times 1, or 6, which is the same as 3 factorial, if you might have learned that from another class. And if you're a little bit lost on this part, don't worry, we are going to get to a second way to count this. And when we finish up this section with Pascal's triangle, we'll get even another way to count something like this. So just bear with me. So we need to do 60 divided by 6, which gives 10 subsets with 3 elements each. All right, so now this value of 10 has eliminated that problem of double counting, or over counting, I guess. All right, but maybe we didn't so much like that way of counting those subsets. So another way would be to kind of think about, well, we just said above that there's 32 subsets total, and those subsets can have any number of elements, right, between 0 and 5, okay? So I'm going to fill all these out. All right, and then we can start in the next row of our table thinking about how many subsets have each cardinality that we just listed. All right, so of course we know that there's only one subset that has 0 elements, and that's exactly the empty set. Likewise, there's only one subset which has all 5 elements, and that's actually the original set A itself. Okay, so we'll put a 1 there, right? So the top row is the cardinality, the bottom row is how many subsets have that cardinality. Okay, well, those ones were kind of the quote-unquote easy ones. I would actually argue that it's easy enough to think of the number of subsets with 1 element each, because those are exactly we call them singletons in math. So this is just how many ways can I choose 1 element from the set and put it in a subset, and that would be exactly these 5 sets. So we can put a 5 right there. All right. I'm going to skip over 2 and 3 for a second and actually go all the way over here to 4. So if you think about subsets that have 4 elements, that's almost doing the opposite of what we just did. Instead of choosing 1 element to include in this kind of singleton subsets, we're going to include which element we want to leave out. So if we leave out the number 1, we're left with 2, 3, 4, 5. If we leave out the number 2, we have 1, 3, 4, 5. If we leave out a 3, we have 1, 2, 4, 5. If we leave out a 4, we have 1, 2, 3, 5. And if we leave out 5, we have 1, 2, 3, 4. And hopefully kind of a quick glance will tell you that these sets that we just wrote down in green are basically the complements of the singleton sets that we wrote down for 1. And hopefully glancing at that you agree that there's exactly 5 of those as well. All right, so we have 1 set with 0 elements, 1 set with 5 elements, 5 sets with 1 element each, and 5 sets with 4 elements each. So how many subsets do we have total? How many have we counted so far? Well, let's see. We've counted 1, 5, 5, and 1, that makes 12. And we know that there was 32 total. So if we subtract those, we have 20 left. So there's 20 subsets, and those have to fit into one of those categories, right? They either have 2 elements each, or they have 3 elements each. So one way to think about this is kind of thinking about the idea of a complement that I mentioned when talking about the subsets with 1 element and 4 elements each. Basically, every time we choose 2 elements, to make a subset with cardinality 2, to make a subset the remaining elements, which is of course 3, so the remaining elements make a subset with cardinality 3. Okay, so take a minute and think about that. If you're choosing 2 elements to make a subset, you have 3 left over. So basically every time you choose a 2-element subset, you're also kind of by default choosing a 3-element subset with the elements that you're not selecting. So what does that mean? Well, hopefully you can agree that that means that there's the exact same number of subsets with cardinality 2 as there are with cardinality 3, right? They match up exactly. So what does that mean? Well, if there's 20 subsets left over and there's the same number with 2 elements as there are with 3 elements, then each of these needs to be 10. All right, now we started with a small enough set. The set A was just 1, 2, 3, 4, and 5, that if you wanted to, you could actually write down all 10 subsets with cardinality 2, and then all 10 subsets with cardinality 3, just to kind of make sure that you believe that. All right, but anyway, this table now kind of tells us the cardinality, of each of the 32 subsets. All right, now we have one more question here. Whoops, that's not the eraser. All right, so the last question is, how many subsets of A contain only odd numbers? Okay, so I'm just gonna jot down set A again so we remember what it looks like. So we're counting the ones with only odd numbers. Well, the odd numbers in this set, of course, are 1, 3, and 5. So in other words, we're asked how many subsets of this set, 1, 3, 5. All right, so we could do, I guess we could do this kind of an easier way. So how many contain only odd numbers? Well, this set now that we just wrote down has cardinality 3, right? And we know that a set with 3 elements, the cardinality of the power set will be 2 to the 3rd, which means it'll have 8 subsets. Okay, but we have to be careful because this includes the empty set, which of course that doesn't have any elements in it, which means it doesn't have only odd numbers. It doesn't have any numbers in it at all, in fact. So we just need to subtract the empty set. So that leaves us with 7. So the answer to how many subsets of A contain only odd numbers, that would be exactly 7. And again, you could write them all down if you wanted to. All right, now, whoops, at the bottom of this page we have, the second page, we have the practice question.